Welcome to this presentation on zero-knowledge proofs. My name is Andrew, and I will be your presenter for today. I'd like to start by acknowledging zklearning.org. zklearning.org was a MOOC given in spring of 2023, presented by the instructors Dan Bonet, Shafi Goldwasser, Don Song, Justin Thaler, and Yupeng Zhang. The presentation today is a summary of the material in that MOOC. The lectures, readings, and coursework are still available on their website. I highly recommend you going there to continue your ZK journey. This presentation is split into 3 sections. First, we'll introduce ZK proofs and show how we get from classical proofs to zkSNARKs. Next, we'll dive into the details of zkSNARKs and show how to construct one. In the last section, we'll look at 2 real-world applications of zkSNARKs in blockchain. Before we start, a quick logistical note. Some slides in this presentation uses higher-level math notation. The purpose of these slides is to formally define concepts previously introduced and are not required for understanding the presentation. These slides have a green dot in the top right. Feel free to disregard these slides if they do not serve you. And with that, let's get into our first section and introduce ZK proofs. ZK proofs were first conceived in 1985 with the paper The Knowledge Complexity of Interactive Proof Systems by Shafi Goldwasser, Silvio Micali, and Charles Rakoff. While research has been ongoing, the interest and development of ZK proofs have recently exploded due to its application in blockchain. With ZK proofs, we can outsource computation, build trustless bridges, and have private transactions on a public blockchain. Furthermore, there are also many non-blockchain applications of ZK proofs that are being looked at. For example, fighting disinformation, credit risk protection, criminal justice, and healthcare. An example of how ZK proofs can be used in healthcare is if we want to prove the health records without revealing the individual or their details. In the field of mathematics and cryptography, there are many types of proofs and proof systems. Each bullet on this slide is unique and has its own field of study. However, since ZK proof is currently a hot buzzword in media, when you see it in the wild, it may refer to any of these ideas. Be aware that they're not all created equal. In practical blockchain applications, only SNARK, STARK, and their ZK variants are used. In this next section, we're going to start with the classical proof, then introduce interactive proofs, and build our way up to the SNARK. Let's begin by looking at the classical proof, which is what most people are familiar with. The construction of a classical proof looks like this. First, you make a claim, then you define some premises, also known as lemmas, axioms, or assumptions. From these premises, you derive logical statements. Finally, you end with a conclusion that either supports or contradicts the claim, and the proof is complete. Here's an example on the right. We start with the claim, the square of an odd number is also odd. Then we define the premise. By definition, if n is an odd integer, it can be expressed as n equals 2k plus 1 for some integer k. From there, we will derive some logical statements by doing math. And finally, we end with the conclusion that since 2k squared plus 2k is an integer, n squared is also odd. This supports our original claim and the proof is complete. Now, let's introduce interactive proofs or interactive proof systems. Here's the setup for an interactive proof. First, you set up 2 entities, the prover and verifier. You can think of these as computers or algorithms. Then a claim is given to both the prover and verifier. The prover then gives a proof to the verifier. The verifier analyzes the proof and decides whether to accept or reject the claim. Let's look at the example on the right. On the left, we have the prover entity in orange, and on the right, we have the verifier entity in blue. The claim, n is a product of 2 large primes, is given to both the prover and the verifier. The prover will generate a proof, which in this case is the 2 primes p and q, and sends it to the verifier. The verifier will analyze it, it'll check that p and q are primes, and then multiply them together and compare the results to n. Finally, if p and q are primes, and their product is equal to n, then the verifier accepts the claim and the proof is complete. There are 2 important properties for proof systems. which are completeness and soundness. These properties help ensure the security and effectiveness of proof systems. The first property is completeness, which is that true claims have a proof. This means that if a claim is true, then an honest prover will be able to convince the verifier to accept. The second property is soundness, which is that false claims have no proof. This means that if a claim is false, then there's nothing a prover can do to convince the verifier to accept. In our example, the claim that n is the product of two large primes satisfied these properties. Completeness is satisfied because if the claim is true, the prover can always give the verifier the two primes that multiply and equal n, and the verifier will always accept. Soundness is satisfied because if the claim is false, then there's nothing the prover can give the verifier to have it accept. Another way of thinking of this is for proof systems to be secure and effective, there cannot be any false negatives, which is completeness, or false positives, which is soundness. Here's our first math slide. We're going to formally define MP proofs, a subset of interactive proofs that are important for blockchain applications. We are interested in MP proofs because it is associated with the classical computer science study of MP complexity problems. To review, MP problems are decision problems that are difficult to solve but can be verified quickly in polynomial time. So the setup to an MP proof is, first we have a prover that is considered computationally unbounded and can do a lot of hard work. We're trying to prove the claim, which is an MP statement to the verifier, who can only run in polynomial time. And finally, the prover passes a witness to the verifier, whose length is polynomial to the length of the claim. Formally defined, a language L is a set of binary strings X that satisfy some property. L is an MP language if there's a polynomial in the length of X time verifier and have the following properties. First is completeness, where if the claim X is in the language L, then there's a polynomial in the length of X long witness W, such that the verifier will accept. The second is soundness, that is, if the claim X is not in the MP language L, then there is no witness. That is, for all witnesses, the verifier will reject. The distinction between MP proofs and general interactive proofs is important for practical blockchain applications, because later we will see that our verifier is actually an L1 blockchain, and we wanted to verify difficult claims in polynomial time that are solved by a more powerful prover. Okay, so going back to our previous interactive proof example, an interesting observation I want to make is that after this interaction, the verifier knows more than they did before the interaction. Specifically, that is, before the interaction, the verifier only knew that n is the product of two primes. After the interaction, the verifier knows the two primes p and q. To make this interactive proof zero knowledge, we want to hide p and q from the verifier. In order to do this, we need to introduce two new concepts to the system: non-trivial interaction and randomness. Non-trivial interaction means rather than passively reading the proof, the verifier engages in a sophisticated way with the prover. Randomness means that the verifier is randomized, or that it can toss a coin, and it can err in accept or reject with a small probability. To show how this works, let's walk through an example. This is the two-color example. Here's the setup. There is a prover on the left that can see color, on the right a colorblind verifier who cannot see color. The claim that is given to both is that this page contains two colors. The goal is for the prover to prove to the verifier that the claim is true without revealing anything about the colors. To execute this proof, first the verifier tosses a coin, and if heads, it'll flip the page upside down, and if tails, it does nothing. The verifier sends the resulting page to the prover. The prover looks at the page and tries to determine whether the coin the verifier tossed was heads or tails. The prover responds to the verifier with a coin toss guess. Finally, the verifier compares the guess to the actual coin flip and accepts or rejects the claim. Let's analyze this proof. If the claim is true and there are two colors on the page, then the prover will know if the page was flipped and can correctly determine the coin toss with 100% accuracy. If the claim is false, and the page does not contain two colors, then the prover can only guess if the page was flipped with 50% accuracy. Furthermore, if the claim is false, and the prover verifier repeated this interaction 100 times, then the probability that the prover will get all 100 correct is 1/2 to the power of 100, which is really, really small. Therefore, if the prover gets all 100 coin tosses correct, then the verifier can accept the claim with very high probability. Now let's look at the zero-knowledgeness of this proof. After this interaction, the verifier has not learned anything new. Specifically, it doesn't know what either of the two colors are. We showed with the two-color example that by using randomness and non-trivial interactions, we can prove the claim with zero knowledge. Furthermore, we can say that by using this technique, all NP statements can be proven in zero knowledge. Now we can redefine NP proofs and say PV is an NP proof for the NP language L if V is a probabilistic polynomial in the length of X and the following two properties are true. First, it is complete. That is, if the claim X is in the NP language L, the probability PV will accept is 1. Second is that PV is sound. That is, if the claim X is not in L, then even for a malicious prover, the probability that PV will accept is less than some negligible amount. To formally define zero knowledge, we say an interactive proof is zero knowledge if, for every claim in L, the real view and simulated view of the verifier are indistinguishable. That is, the real view, or what the verifier knows after the interaction, is indistinguishable from the simulated view, or what the verifier could figure out before the interaction. So in conclusion, PV is a zero-knowledge interactive proof if it's complete, sound, and zero knowledge. Okay, let's review. At a high level, interactive proofs look like this. The prover solves a problem and tells the verifier the answer. Then they have a conversation. The prover's goal is to convince the verifier that the answer is correct. All interactive proofs must satisfy these two properties, completeness and soundness. Completeness means an honest prover can convince the verifier to accept. Soundness means that the verifier will catch a lying prover. Optionally, we can make any interactive proof zero knowledge by adding randomness and non-trivial interactions. Next, let's look at the interactive argument of knowledge. An interactive argument is an interactive proof where soundness only holds against polynomial time provers. That is, the soundness property of an interactive argument is based on cryptographic assumptions, such as you can't reverse the SHA-256 hashing algorithm. This is fine today because all of our computers run in polynomial time. However, note that this means interactive arguments may not be post-quantum secure. If in the future we have a malicious prover that is a quantum supercomputer, then our proof system may not be sound and the prover may be able to convince the verifier of a false claim. The second concept is knowledge soundness. Previously, when we talked about soundness, we meant standard soundness, where if the verifier accepts, then there exists an answer to the claim. Contrast this to knowledge soundness, where if the verifier accepts, then the prover knows the answer to the claim. The difference between standard soundness and knowledge soundness is very nuanced, but the main takeaway is that knowledge soundness is a strictly stronger statement than standard soundness. It is important to blockchain applications because we want our proof systems to guarantee that the prover actually knows the answer to a problem, such as the prover knows the secret of a wallet, and not just that it exists. Finally, we can put it all together and get the zero-knowledge interactive argument of knowledge. We now have a proof system where a prover can convince a verifier with high probability that the prover knows the answer to a claim without revealing anything about the answer. Now, let's look at one of the most popular categories of proof systems, zkSNARKs. Let's start by talking about why these proof systems are so important. In 1991, there was a paper published by Babai, Fartnow, Levin, and Szegedy, where they say that with these proof systems, A single reliable PC can monitor the operation of a herd of supercomputers working with unreliable software. Now, back in 1991, we weren't sure what practical applications this had. Fast forward to today, we now can see that an L1 blockchain fits the description of a single reliable PC, and GPUs fit the description of supercomputers. So we can update the statement and say, with these proof systems, an L1 blockchain can monitor and verify the operation of a herd of untrusted GPUs. Although today we'll be focusing on SNARKs, I want to note that there's a lot of research and development being made into other zero-knowledge proof systems out there today, such as SNARKs, bulletproofs, and especially STARKs. The industry is still experimenting with and figuring out the trade-offs between these different proof systems, and new proof systems are being discovered every day. This is an active and ongoing area of research and development. With that being said, let's define SNARK, which stands for Succinct, Non-Interactive Argument of Knowledge. SNARK is a category of proof system with the following properties. They are succinct, which means the proof is short and fast to verify. They are non-interactive, which means every verifier can independently verify the claim without talking to the prover. They are arguments of knowledge, which means the prover knows the information with high probability and based on cryptographic assumptions. Optionally, they can be made zero knowledge. I want to emphasize that the main advantage of SNARKs and the reason for their popularity is their succinctness. Succinctness makes the proof size, or the amount of data that you need to pass to the verifier, very small. It also makes the proof quick to verify. For example, Ethereum transactions have a maximum limit on how much data you can send and how long the transaction takes to complete. In order to send a proof and verify it on the blockchain, then the proof must be succinct. To construct a SNARK, use the following two components. An interactive oracle proof, or IOP, which is the protocol the prover and verifier use to talk to each other, and a commitment scheme, which is an algorithm that condenses the IOP and makes it succinct and zero knowledge. Finally, you can make the proof system non-interactive by performing the Fiat-Shamir Transform. Now let's look at each of these individually. We'll start with the interactive oracle proof, or IOP. An IOP is a system of constraints or equations that can be proved and verified. The system of constraints is the language of the proof system. These constraints are implemented as arithmetic circuits. A popular format is Rank 1 Constraint System, or R1CS. These circuits define what set of statements are possible. Here are some common programming languages and libraries for implementing arithmetic circuits. The first way to implement circuits is by using a hardware description language, or HDL, the most popular being CIRCOM. HDLs are low-level languages where you construct circuits from the ground up. You can think of HDLs as writing assembly code in classical programming. The next way is by using libraries of high-level languages. The benefit here is that you can write your code in a familiar high-level language like Rust, C++, or Go, and use their language features like data structures and loops. The trade-off is that when your code compiles down to circuits, they tend to be larger in size and less efficient than HDLs. The third option is domain-specific languages, or DSLs, which tries to combine the best of the two previous examples. DSLs are high-level languages that are specifically designed to compile down into circuits. The benefit is that you can use language features like data structures and loops while still having it compile into an efficient circuit. Let's look at the formal definition of an arithmetic circuit. Given a finite field F with the elements 0 to p minus 1 for some prime p, an arithmetic circuit C takes n elements of the finite field F and produces another element in F. Arithmetic circuits can be thought of as DAGs, where the internal nodes are labeled as plus, minus, or multiply, and the inputs are labeled 1, x1 to xn. Arithmetic circuits define an invariant polynomial, and when we say the size of a circuit, we are talking about the number of gates or constraints that it has. Looking at the image on the right, you can see that at the bottom we have a DAG with the leaf nodes x1, x2, and 1, and the internal nodes plus, minus, and multiply. This DAG represents the polynomial x1 times the quantity x1 plus x2 plus 1 times the quantity x2 minus 1. Let's look at two examples of arithmetic circuits. The first is C-SHA, which is a circuit for verifying the SHA-256 hashing algorithm. C-SHA takes a hash h and a message m, and returns 0 if SHA-256 of m is equal to h. Otherwise, it returns non-zero. Implementing C-SHA would take about 20,000 gates. The second is C-SIG, which takes a public key pk, a message m, and a signature o. C-SIG returns 0 if o is a valid signature on the message m with pk. The size of C-SIG is about 1.5 million gates. As I mentioned previously, R1CS is a popular format of arithmetic circuits used in ZK Proof implementations. The R1CS format is defined as X, which is the set of public inputs, W, which is the set of private witnesses, and most importantly, the circuits implement equations with the form alpha times beta equals gamma, where alpha, beta, and gamma are affine combinations of variables. Any circuit can be turned into the R1CS format, and the benefit of R1CS is that it makes the construction of complex gates easier, and why it is preferred and used in many SNARKs. The next component of a SNARK is the commitment scheme. A commitment scheme is essentially an algorithm that takes an IOP, which is a large set of equations, and condenses them into something short and quick to verify. This act of condensing of the IOP using commitment scheme is known as a pre-processing step or setup step. Commitment schemes are necessary because it takes the IOP and makes it succinct and zero knowledge. In practice, a commitment scheme can be thought of as a hashing algorithm. There are two broad categories of commitment schemes. The first are trusted setups. Trusted setups are trusted because there's a magic number that is used as part of the setup step. You have to trust that the magic number is destroyed and forgotten after setup, because if the magic number gets leaked, then a lying prover can prove false claims. The most popular example of a trusted setup commitment scheme is KZG. KZG was used for Ethereum's proto-dink sharding feature, and the summoning ceremony was a way to create and destroy the magic number in a decentralized way. The second category are transparent setup commitment schemes. Transparent setups are transparent because they don't require the using and destroying of a magic number. The setup can be done transparently in the open while still maintaining security. The trade-off between trusted and transparent setups is how fast and small the resulting SNARK is at runtime. You will see that the trusted setups are often orders of magnitude more efficient than the transparent alternatives. Formally, commitment schemes are a general concept of committing information. For SNARKs, we are interested in commitment schemes for IOPs, which are previously defined as arithmetic circuits representing polynomials. Therefore, we are specifically interested in polynomial commitment schemes. A formal definition of a polynomial commitment scheme is as such. A polynomial commitment scheme is defined as a set of four functions. The first is a keygen function, which can optionally take a random number lambda for a trusted setup and a set of equations f, or the IOP. This produces the global parameters GP. Next is the commit function, which takes the global parameters and a single function in f and produces a commitment to that function. The third is eval, which is run by the prover and takes a function f, an input u, and produces v and a proof pi. And finally, verify, which is run by the verifier, and this takes the commitment to f, u, v, and pi, and will either accept or reject. Note that we can hide the input u from the verifier and make this zero knowledge by using the techniques previously described. Polynomial commitment schemes have two properties. The first is binding, which is that the commitment to f evaluates to exactly one output v for every input u. And the second is hiding, which is that the commitment of f reveals nothing about the function f. So finally, we can say that when a prover commits to a polynomial f of x in the IOP f with degree at most d, for the elements u, v in the finite field f, the prover convinces the verifier that f of u equals v when the verifier only has d, a commitment to f, u, and v. The proof size and verifier time is O of log d. By applying a polynomial commitment scheme on an IOP, we can make it succinct. That is, the output size of v and pi are very small, and the runtime for verify is quick. Furthermore, because of the hiding property of polynomial commitment schemes, we can make this protocol zero knowledge. Finally, to make any interactive protocol non-interactive, we can apply the Fiat-Shamir Transform. Instead of the verifier flipping a coin to create randomness, the prover can generate randomness themselves using a hash function. So let's look at the public coin interactive protocol, which is what we've seen before. Here, the prover sent the verifier a message, the verifier flips a coin and sends back a challenge, and the prover responds to that challenge. You can repeat this 100 times. With Fiat-Shamir, the prover will take the original message and hash it. Then it uses that hash as a challenge and generates a response. It can then hash the response and use that as the next challenge, and repeat this 100 times. Finally, it'll send the original message, all 100 hashes, and all 100 responses to the verifier. We've made it so that instead of having the verifier send challenges to the prover is able to generate a series of random enough challenges that the verifier can independently verify and accept with high probability. By applying the Fiat-Shamir transform, we can make any interactive protocol non-interactive. This is useful because it enables us to prove a claim to a lot of people without having to talk directly to all of them, which is exactly what we want for decentralized blockchains. Okay, let's finally put it together. To build a SNARK, first, the prover and verifier agree on a system of constraints. This is the interactive oracle proof, or IOP. Then the IOP is pre-processed and made short and fast. This pre-processing algorithm is the commitment scheme. You can remove interaction by applying Fiat-Shamir transform. You put it all together and you've got a SNARK. Then with a SNARK, you can apply some common transformations to the commitment scheme to make it zero knowledge. To formally define a zkSNARK, it is a proof system with the following three algorithms. First, a setup algorithm that takes a constraint system C and optionally random number R for trusted setup and outputs the public parameters PP and VP. A prover algorithm that takes the public parameters PP, a public claim X, and a private witness W, and outputs a short proof pi whose length is at most log of C. And finally, a verifier algorithm that takes the public parameters VP, public claim X, and proof pi, and it will either accept or reject the claim in time of log C or the length of X, whichever is longer. Let's look at some popular commitment schemes and their performance trade-offs. The first one is KZG, a very popular trusted setup commitment scheme. You can see that the benefit of KZG is that you have a constant proof size and constant verifier speed. The other four examples are all transparent setups. Notice that their proof size and verifier speed are all worse than KZG. It should be noted that not every commitment scheme is appropriate for every single use case. In general, the common factors to consider when looking at commitment schemes are efficiency, proof size, setup requirements, security model, and its applicability to your use case. You can sort of plug and play different IOP and commitment schemes together to generate different SNARK systems. Here's an example of 3 SNARK systems built off the Plonk IOP. You take the Plonk IOP with KZG, you get Aztec and Jellyfish. You take Plonk IOP with bulletproofs, you'll get Halo 2. And you take the Plonk IOP with the Fry commitment scheme, you'll get Plonky 2. Finally, we can compare some popular ZK proof systems. Groth16 and Plonk Marlin are both SNARKs that use a trusted setup, which result in a constant time proof size and constant verifier speed. Bullet proofs and SNARKs are other proof systems. They both have transparent setups, but as a trade-off, their proof size and verifier speeds are orders of magnitude larger than SNARKs. Now that we've learned what a zkSNARK is, let's look at two real-world examples using it. Our first example will look at ZK rollups, a layer 1 scaling solution. Here we have a traditional L1 blockchain. There's a network of computers or nodes that communicate with each other. A user will send transactions to one of these nodes, which get bundled together into a block and proposed to the network. Each node will independently verify the proposed block, and if consensus is reached, the block will be added to the blockchain and the process repeats. The benefit of this process is that it's secure and decentralized. However, the trade-off is that it's extremely expensive and slow. ZK rollups attempts to solve this by using a ZK proof system. In ZK rollups, there's a centralized prover that can process significantly more user transactions at a much faster speed. The centralized prover will generate and submit a zero-knowledge proof to the L1 blockchain, saying what the final outcome of all the user transactions are. The L1 blockchain nodes can all independently verify the proof succinctly and without interaction. The soundness property of the system ensures that a lying prover will be caught and rejected. Thus, we can increase the throughput of transactions significantly with this method. Examples of projects doing this today are zkSync Era, Scroll, and Aztec. The second example we'll look at are ZK bridges, a trustless way to communicate between blockchains. Traditional bridges work by using an intermediary that reads data from the sender chain and then communicates it to the receiver chain. Popular types of intermediaries today are sidechains, committees, and oracles. However, each of these make a trust assumption in order to ensure correctness of the message. We've seen numerous instances where these trust assumptions are broken. For example, by having the private keys of committee members stolen results in millions of dollars lost. With ZK proof systems, we can create a prover-verifier protocol where the centralized prover reads the most recent 2 blocks of the sender chain and generates a proof that includes the state changes of these blocks. This proof can be given to a smart contract on the receiver chain, which can efficiently verify the proof and mint new tokens. For example, a prover can claim that 100 ETH was deposited into the bridge between block height T and block height T plus 1. It will generate a proof and submit it to the receiver chain, which will verify and respond by minting 100 ETH. The benefit of this system over traditional intermediaries are that it replaces trust assumptions with cryptographic soundness. We can have efficient on-chain verification because of SNARK succinctness. And finally, we can onboard provers in a permissionless and decentralized way, since provers don't have to be trusted. That's the end of the presentation. Thanks again to zklearning.org, and special thanks to Francisco Ignacio and Danny Villardo for their feedback. Thank you.